Hello everyone, I'm Xiaojian from Tsinghua University. Today, I will present our work Crash-Consistent Non-Volatile Memory Express. Crash consistency is an important topic in storage systems. It represents the atomicity of a single operation that updates multiple blocks despite a sudden system crash, such as a power outage. For example, suppose there is an operation that consists of two blocks from the host to storage. Only two cases are valid for a crash-consistent storage system. The first case we term as O. Before crash, all the two blocks are stored in the persistent medium. Nothing needs to be done after crash. The second case is nothing, that is, none of the blocks are persisted. Suppose the D block is lost during the crash. During the next system boot, the host recovers the system to a consistent state by discarding the M block. Another vital topic along with the crash consistency is storage order. It defines the persistence order of multiple individual operations or transactions despite a sudden system crash. For example, the host sends two transactions to the storage, and transaction 1 must be persisted before transaction 2. Suppose a crash occurs during the transfer of the two transactions. After crash recovery, three states are valid, all of which obey the persistence order. Most storage systems use journaling to achieve crash consistency and storage order. We use an example to illustrate the journaling. The workload is creating and writing a new file. A transaction consists of four kinds of data blocks: D, JH, JM, and JC. The host first sends D, JH, and JM to the storage. Then it issues a barrier, such as the flush command, to ensure the blocks in the volatile buffer are flushed to the persistent journal area. Next, it persists the JC to enforce the atomicity of the transaction. After all blocks are persisted in the journal area, the storage systems checkpoint the blocks to their home location. In the face of a sudden crash, the storage system can replay the blocks in the journal area to achieve crash consistency and storage order. Persisting a block mainly consists of four parts: submission, block DMA, completion, and the barrier. Two ordered transactions are processed serially with a barrier in between. We find two major issues of journaling. The first is the extra storage traffic, including the extra MMIOs of submission and completion. Irrelevant blocks incurred by the device-wide flush, and extra commit record generated by the journaling. They consume the available bandwidth of SSD provided to the host software. The second is the serialization of ordered transactions, which poses long latency to each transaction and conflates atomicity and storage order with durability, increasing the transaction latency. To address these issues, we propose CCNVMe, a generic storage protocol that provides crash consistency per hardware queue storage order and high performance. First, CCNVMe reduces unnecessary storage traffic, including the commit record, one flush command, and MMIOs. Second, CCNVMe prioritizes ordered transactions by separating atomicity from durability. Using our proposed F-atomic interface, storage systems can ensure crash consistency and storage order with only two MMIOs over the PCIe. CCNVMe is designed as an extension of NVMe atop persistent memory region-enabled SSDs The left picture presents the traditional NVMe storage stack. The right picture shows the CCNVMe storage stack, which uses the persistent memory region feature of the original NVMe. The PMR can be capacitor-backed DRAM, 3D XPoint, or other persistent memory, and can be accessed directly by the CPU load and store instructions. Atop the driver, we design a no-journal file system which exposes an extra Atomicity primitive to support atomic transactions. Applications can also issue raw CCNVMe commands to ensure atomicity. We observe that in the original NVMe, the submission queue and doorbells check the life cycle of each request. To store a block, the host first places an NVMe command in the SQ, followed by ringing the SQ doorbell. Note that at this time, the request is about but not yet to be processed. The storage device then fetches the command and transfers the data block. After the device finishes processing, it places a completion entry in the CQ and generates an interrupt. The host then consumes the completion entry and rings the CQ doorbell. Note that this indicates that the request is completed. Inspired by the NVMe workflow, we decide to let crash consistency and storage order take the free rise of the data dissemination mechanism of the original NVMe. Specifically, CCNVMe places the SQ doorbell, and SQ head value to the PMR to record the life cycle of all in-progress requests. CCNVMe then transfers the NVMe commands and data payloads in the unit of a transaction. First, we introduce transaction-aware MMIO to send the NVMe commands in a large batch. Second, we introduce transaction-aware doorbell to ring the doorbell in the unit of a transaction to let the requests from the same transaction reach the same stage. The other procedures are kept the same as NVMe. Transaction-aware MMIO is based on the persistent MMIO write, which takes three major steps. First, the host uses CPU store to store the command in the write combining buffer. Second, the host issues cache line flush to flush the commands from the WC buffer to the PCIe load complex. Finally, exploiting the PCIe ordering, the host issues an extra PCIe read to persist the command to the PMR. As the overhead of persistent MMIO is expensive, transaction-aware MMIO is introduced to batch MMIOs of each transaction. The key idea is to postpone the cache line flush and PCIe read. Suppose a transaction consists of 3 blocks. The host stores 3 NVMe commands to WC buffer and issues only one final flush and PCIe read to ensure persistence. Transaction-aware MMIO improves the PCIe access efficiency, as large persistent MMIOs brings higher bandwidth and reduce the overall transaction level latency. As a transaction is completed only if all of its requests are finished, CCNVMe only rings the SQ and CQ doorbell once for each transaction to let the requests of each transaction reach the same state. The transaction-aware doorbell reduces the SQ doorbell MMIOs to 1 and removes the commit record. The SQ doorbell essentially serves as the commit point for a transaction. Similarly, CCNVMe rings the CQ doorbell once. Note that before ringing, CCNVMe stores the head value of SQ to indicate that the requests prior to the head pointer are finished. In the face of crash recovery, CCNVMe provides non-atomic and out-of-order transactions to upper-layer systems to handle these unfinished transactions. For example, the file system can discard the unfinished transactions. In the picture, the blocks between the SQ head and SQ tail are unfinished. The storage system can directly drop this data content in the journal area. In summary, CCNVMe provides crash consistency by the transaction-aware doorbell, as transactions are submitted and completed atomically. CCNVMe provides storage order by in-order doorbells, as for each hardware queue, the doorbells are set in order. CCNVMe provides crash consistency and per hardware queue storage order. We further introduce multi-queue file system to take full advantage of CCNVMe. When fsync or fatomic are invoked, MQFS dispatches transactions to each hardware queue for crash consistency. To reduce the CPU overhead, each hardware queue has its journal area, and each core can send the transactions to its dedicated hardware queue and journal area with less log contention. Note that the file system should control the global storage order among multiple hardware queues. Other details, including the detailed CCNVMe IO commands, metadata shadow paging of MQFS to persist shared blocks in parallel, selective revocation to handle block reviews across multiple queues, and implementation details are presented in paper. We report the results of CCNVMe against classic and state-of-the-art systems atop recent Optane SSDs and multi-core servers. We first present the performance of persisting transactions. During the test, each thread persists independent transactions. The x-axis shows the size of data content of each transaction, and the y-axis shows the throughput. In CCNVMe Atomic, the thread ensures only the atomicity but does not wait for the durability. We observe that CCNVMe outperforms its peers significantly. The separation of atomicity from durability further improves the throughput. We conduct the same test by increasing the threads. Due to the reduction of PCIe traffic, CCNVMe prevails its peers when the SSD bandwidth is saturated. Now, we report the application performance. In the legend, the MQFS is our proposed file system that utilizes the crash consistency and storage ordering guarantees of CCNVMe. We find that MQFS significantly outperforms its counterparts. The throughput of MQFS comes close to or even surpass ext4 node journal that does not provide crash consistency, as MQFS provides higher CPU and I/O efficiency. In summary, we propose CCNVMe to provide generic crash consistency and storage order inside the storage protocol. We conclude that storage systems should separate atomicity from durability and reduce the CPU overhead to fully exploit the high concurrency of modern NVMe SSDs. That's all. Thank you for listening.